One way I start every class of mine is that I start by telling the students, and I do it both on the college level. I tell the teachers to do it in their classes, probably starting from 6th grade. Telling the students to bring in articles from a newspaper, from a magazine, from a comic book that has to do something with science. For example, there is a story, a medical story about skin cancer. Then I'll discuss with the class why is the percentage of skin cancer now higher than it was before. The class will come with a conclusion that it's because the depletion of the ozone layer. The ozone is protecting us from the bad radiation from the sun. We deplete the ozone. This is why we have this problem. Then we start discussing what is ozone. Ozone is a molecule. What is this molecule made of? It's made out of 3 atoms of oxygen. There is the oxygen we breathe. Oxygen we breathe is 2 atoms of oxygen. Then we get to the discussion how the ozone up there in the stratosphere is extremely important for our life to protect us from the destructive UV radiation so we don't get the skin cancer. Then we come to the discussion that ozone here in the atmosphere, if we breathe it, if we have ozone layer because of smoke and other pollution in the air, it's very bad for our health. And the students must distinguish between the ozone that is pollutant when it's in the air and the ozone that protects us from the radiation of the sun. For example, if we discuss, and a student will bring an article, Chicago is surrounded by nuclear power plant. So there are all the time articles on nuclear power plant. So then the discussion starts. What is the nuclear power plant? Why is it called nuclear? The students for the first time realize that they don't have any idea. So we discuss the fact, coal power plant. How do we get electricity? We burn coal. Oil power plant. How do we get electricity? We burn oil. Nuclear power plant. How do we get electricity? There will always be students that will say, burning nuclear. What is nuclear? Suddenly a big puzzle. Nuclear, what can it be? We go through a discussion. Maybe it's a nucleus. A nucleus of what? A nucleus of an atom. Atom, what is an atom? What is made up of atoms? Everything is made up of atoms, everybody will answer. So let's look at the room. What is made out of an atom? The air we breathe, the chairs, and then I remind them, you are made out of atoms. So then the question is the atom electrically charged or neutral? Are we electrically charged or neutral? Can we go straight through an electric field or we are pulled to one side? We come to the conclusion that we are neutral. We are discussing the electrons, protons, and the nucleus of the atom, that the nuclear power comes from the nucleus, and then we go into the discussion from there, what is a chemical bond? But all that is the result of the articles in the newspaper that the students relate to, that they are relevant to their environment, they are relevant to their life. They see the importance of that, and they see how important for them it is to understand it. Then comes the other issue that here Chicago has nuclear power plants. Sometimes we hear there is radiation. We discuss that. But then we have to discuss why we have to understand it in order to live in a democracy and participate in the democratic process. And by participating in the democratic process, we vote for candidates. We have to know what these candidates say about nuclear power plants, especially around Chicago. What do they say about energy policy? What do they say about different pollution? What do they say about radioactive waste? What do they say about protecting the atmosphere? Once we understand all these issues, we can participate in the democratic process. And it's extremely important to explain to the students that each of them makes a difference if they understand and they try to participate. So, okay, let's see how we really get molecules. And with that, we start by looking at the big periodic table that we have, or I hand out to students different periodic tables so they have it. And we start by that. Here is the noble gases: helium, neon, argon, krypton, xenon, and radon. They are noble, inert, and really they like to be single. They don't have to get involved with another atom or another element in order to be stable. They are very stable. They are very happy to be single. And I explained to the students that when the scientists looked what is different between these elements and the rest of the periodic table, they found that each of them, excluding helium that is on the top, has 8 electrons in their outer shell, as we can see it from the periodic table. From that, the scientists came to the conclusion that if an atom has 8 electrons in the outer shell, the atom must be stable. But because all the rest of the atoms in the periodic table don't have 8, they must get married to somebody else, form a molecule to be stable. And for example, I usually like to start with an element that the students recognize. For example, table salt, that is sodium chloride. So I write on the blackboard sodium chloride. And then I ask the class. I usually tell my class to answer me as a choir because I don't like only one person. It's very easy to see who doesn't understand when the class talks as a choir. So I'll ask them, how many electrons does sodium have? They all will be very happy to say 11. Now we go through the explanation how the electrons occupy the levels, as we saw on the periodic table on the side, the numbers. So all the students know that the first level can have maximum 2, the second level can have maximum 8. So for sodium, we have 1 on the third level. Then I asked them, how many electrons does chlorine have? The whole class is happy answering me as a choir, as a chorus, 17. How are these distributed? 2 on the first, 8 on the second, and 7 electrons in the outer shell. We just learned that in order to be happy, stable, they have to have 8. So sodium is very unhappy by itself. Chlorine is very unhappy by itself. But then the second question to the students is, what does this number 11, that is the atomic number, tells us? The students already reviewed it before when I explained to them. They know that the 11 tells us that we have 11 negative particles called electrons and 11 positive particles called proton, and therefore the atom is neutral. Now, in order for sodium to be happy like neon, that is the noble gas before him with 10, he has to get rid of this 1 electron that he has, and then he's left with 8. Sodium happily gives its electron to chlorine, and now both of them are happy. Sodium has 8 electrons in the outer shell, and chlorine has 8 electrons in the outer shell. But something happened to the balance between proton and electrons. And what happened is that if sodium had 11 electrons and 11 protons and was neutral, it has now 10 electrons and 11 protons, what makes it 1 more positive particle than negative, and sodium become positively charged and is called an ion. Chlorine that had 17 electrons and 17 protons has now 18 electrons and 17 protons, and because of that, chlorine has one more negative charge, and because of that, chlorine is now charged negatively. And here comes the attraction. We know that opposites attract, so the positive sodium and the negative chlorine attract each other, and we are getting table salt. That is the salt we are using, sodium chloride. And the bond between the sodium and chlorine we call ionic bond because it's attraction between ions. Now, what happens to table salt when we put it in water? Because water has a polar ability, then the sodium and the chlorine separate because of the polarity of the water, and practically the ionic bond breaks. But when we evaporate the water, then the crystals have again the sodium chlorine. And this is an ionic bond. The way we usually write it, what we tell the student, is we write it in a dot system where we show the number of electrons in the outer shell. 7 for chlorine and 1 for sodium. And then we show how the electrons move from each other. And this is the story of an ionic bond. And this explains was the metals from this side of the periodic table and the halogens that are fluorine, chlorine, bromine, iodine, like in the periodic table that every student has in front of them. So these are the metals that are ready to give electrons. These are the halogens that are ready to get, and they are forming the salt with an ionic bond. Usually, I tell the students that they don't have to memorize the name of the elements like they did and hated it in school when they studied it. Because I try to tell them a secret that the elements don't know their name. And it's only committees that give them names. And this is good because it's occupied our chemists in committees to assign names to the element, and it's easy for the chemists and the scientists to talk to each other when they need it. But it's more important to understand what it means and not just to memorize name of the periodic table. And again, the students can see that the noble gases, they are the royalty because they like to be single, they are very stable and very happy the way they are. But then I move to the second kind of a bond that in nature we find in all the compounds that make out our body, all the organic materials. And this is called a covalent bond, when atoms share electrons. And we look again, and we take, for example, oxygen. I ask how many electrons does oxygen has? The whole class as a course answers 8. How are they divided? 2 in the first, 6 in the second. Then we do the dot system. 1, 2, 3, 4, 5, 6. How many electrons does oxygen want in order to be stable like the noble gas? The whole class sees immediately 2. Hydrogen, that wants to be like the noble class helium, that has only 2 electrons, hydrogen has only 1. So here is hydrogen with its 1, ready to share its electron with oxygen, and instead of giving the electrons to each other, they share it. Then comes hydrogen from the other side, and then the class together says, oh, oxygen now sees 8 electrons, very happy, resembles neon, the noble gas. Hydrogen now sees 2 electrons, is very happy, he like helium. So everybody is happy for this combination, and everybody gets their 8 electron in the outer shell. But this kind of bond where they share electrons is called covalent bond. The same is, we will go to nitrogen. Nitrogen has 7 electrons. The whole class does it together, 2 and 5. Then we do the dot system, 1, 2, 3, 4, 5. And the whole class says nitrogen needs now 3 hydrogens in order to be stable. Nitrogen has 3 covalent bond. Nitrogen now happy sees 8 electron, and this is ammonia with 3 covalent bonds. And we move to carbon, and carbon has 6 electrons. So the class together will say 2 and 4. Our carbon has 4 dots. Carbon now needs 4 more electrons, so 4 more hydrogens will come and share electrons with carbon. Carbon now sees 8 electrons. Every hydrogen sees 2. And everybody is happy, like the noble gases. And carbon formed 4 covalent bonds. Covalent bonds are very stable, very strong, very hard to break. And here, in a very easy way, the students understand why we have molecules, why we have covalent bond. All the elements want to be noble, inert, and free. So in order to do that, they have to get married to each other, share electrons, and the sharing brings them stability.